Good morning, everyone. My name is Gavin Lewis, and I'm the host this morning for the Fathom FabDEM webinar. And we've got two colleagues and guests who are going to be presenting with me, which I'll talk about in a minute. Just a little bit of housekeeping. We have plenty of time for questions at the end of the presentation. So if you do have any questions, and I hope you do, then please add your questions to the Q&A panel and submit those to me. I will be pulling out the questions at the end and going through them. So please provide those questions as you go along. Excellent. So let me just introduce the other speakers on the call. I'm joined this morning by Dr. Laurence, who's the Senior Research Associate at Bristol University, and also my colleague Pete Huey, who's one of our senior developers at Fathom. And my role at Fathom as Head of Engineering is really to take our data and products out to our engineering clients and partners and end users and ensure they get the best out of Fathom data. Right, well, let's have a quick look at the agenda this morning. I'm going to do a short introduction as to who we are at Fathom and what we do. And then I'm going to be handing over to Laurence to talk about the development of FabDEM. He's going to be followed very shortly by Pete, talking about the comparisons of FabDEM. And then I'm going to come back and talk a little bit about the actual applications for FabDEM and some of the information on the data set. And then we'll be getting into the question and answers after that. So, without further ado, let's start. So, Fathom have been around since 2013. It was set up by two guys doing their PhDs at the world-renowned Flood Research Unit at Bristol University. And during their PhD, they felt that looking at the flood models and the availability of flood models globally, they could probably do a better job using the research they were involved in. And so really the ethos of Fathom has been built around providing a much better understanding of flood risk at a global scale using big data, but really underpinned by research. And that underpins everything we essentially do. So we've got a very robust research pedigree. Everything we create, models and data sets, we publish in world-renowned peer review, world-renowned journals, and we are very open, and we make all those papers available on our website. And so if there's anything that you'd like to understand around our data or our models, you'll find it on our website, and I would encourage you to go there and look at our papers, and I'm sure there may be questions that they raise, and please come back to us with those questions. So you can see there we've got a good pedigree, and we've produced 3 papers already this year. Okay, so what do we actually do at Fathom? Well, we essentially create computational flood models. We effectively produce data that tells people what's going to get wet during a flooding event or different types of flooding events at a global scale, but also down to a local scale. And we have essentially 3 product lines. The first one is the hazard data, or the hazard maps, as you can see here in this animation of the river in the US, where we take a lot of data, remote sense data, and produce very detailed flood maps at a global scale all the way down to a local scale. Now that allows us to give a very good representation of behaviour of water during different types of flooding events. So whether that's a river flooding, whether that's flash flooding or coastal flooding. Once we've created those data sets, that's allowed us to then develop stochastic or CAT models, which we have done for the insurance market. And that allows us to create from the elements of the flood map to create effectively an event set, a synthetic event set, looking at the vulnerability of properties to flooding, for us to then to calculate a financial loss or average annual loss to assets due to flooding. So we have those two key elements of the flood maps and the flood models. Now, all of that is going to be underpinned by the data we pull into into our modelling framework to create the detailed information that we provide to our customers and partners. Now, of course, a lot of that is really important, and one of the key elements for any flood model is going to be the terrain data. We all know water runs downhill, so we need to know where downhill actually is. So by pulling in or creating as detailed terrain data to develop our flood models is absolutely critical. And that's what we've done here. We're going to talk a little bit more about FabDEM, how it's created, and actually why we've created it is a good question. We have used it it's going to underpin our new global hazard data set, Fathom Global 3, which we'll be releasing later on in the summer. And that takes from our current 90-meter resolution, we'll take our global hazard data set to 30-meter resolution. And will include inland flooding as well as coastal flooding and a whole variety of climate change scenarios as well. Okay, let me just hand over now to Laurence, who will be able to talk to you about the development of FabDEM.
Thank you very much, Gavin. Thank you everyone for coming. I know some of you have got up very early this morning and staying up very late. So I'm going to be talking about the why we developed FabDEM and how we developed FabDEM. So a lot of this is outlined in our paper, which is in environmental research letters, and is open access as well. So you don't have to be subscribed to this particular journal. So I think it's good to take a step back and tell everyone here how I kind of fit into this jigsaw and what kind of the motivations are. So I'm a postdoc at the University of Bristol. I've done my PhD also at the University of Bristol with Paul Bates and Jeffrey Neal. And I essentially work on regional flood models in data sparse areas. So I've worked across Africa, Vietnam, and one of the key components, I can believe the key component in creating a good quality flood model is a digital elevation model. So what is a digital elevation model? So quite simply, it measures the elevation of the Earth, and it's usually in a gridded product. So I think a really nice way to think about this is if you look out the window now, where you are, and divide the areas that you can see into imaginary like 90 by 90 meter squares, say, or 30 by 30. And each of those little squares has an elevation value. So it might be, and this is usually above a datum, so usually mean sea level or a national datum. So imagine this covers the whole world. Create these little grids, and these are what are used in the computational flood models to give something like which was just shown in the last slides from Gavin. Next slide, please, Gavin. Great. So I was working on a project in Vietnam, and we had tandem X data, which was 12-meter resolution. And the original plan was to correct this for flood inundation models, so removing the artifacts. But we only had a very small area because it's only allowed a small amount of scientific research. But then the Copernicus Glow 30 DM was released in 2020. So this covers the whole world at 30-meter resolution. And we did some comparisons to your existing global DEMs, so the ones that probably a lot of people on this call use, SFTM, Merit, ALOS, ASTER, NASA DEM, you kind of name it. We did some kind of ad hoc comparisons. We didn't publish any of this, but other people have. And this is a really nice quote from this paper here from Goof and Jeffroy. It says, Copernicus Glow 30 should become the gold standard of DEMs, which I have to say I agree with. However, there's a slight problem with Copernicus DEM, and that is a digital surface model. So what does this mean? I think this bottom diagram shows this quite nicely. So the dotted line here represents a digital surface model. So this measures the elevation of the Earth's surface. So this might be a tree, might be a building, might be an electricity pylon, kind of any artifact that's on the surface. However, this is not useful for so many applications. Most applications that are used in the geosciences, such as flood modelling, is kind of quite obvious one, and there's also things like landslide modelling, animal migration. There's a whole host of different applications. Need something called the digital terrain model, and this measures the elevation of the ground. What we need, next slide please, Gavin. So these digital terrain models, or DTMs, are only available, so you can get high quality ones from LiDAR. This is only available for a tiny proportion of the world. In 2018, we estimate this to be 0.05% of the Earth's land surface. Sorry, can you go back? So we need a global DTM to fill in these gaps. And to date, the best one probably for this job was the FabDEM, which is a 90-meter resolution, and that's a major correction of SRTM, and it removes forest as well, but no buildings. So with all this in mind, we kind of thought the time was right to make the next step change in global DEMs. So we came up with three aims essentially. So we wanted to take the Copernicus DSM as a base product because it's substantially better than anything else out there. We wanted to remove trees from that. We wanted to remove buildings, and by doing so, become the first global DEM to do this. And also apply some state-of-the-art image filters to remove erroneous noise from the Copernicus DEM. Next slide, please. Right, so to do this, we use a machine learning approach, and we went down the random forest line. So a lot more of this is described in the paper, but I'll just do a quick whistle-stop tour of this. So the workflow is in three sections, really. The first of all is data preparation. So machine learning here needs predictor data, so essentially to estimate the forest heights and the heights of buildings. So we did a trawl of the literature and the latest data sets out there, and we came up with this set. So, for instance, we have forest heights. This table here, which is based on JEDI, which is a LiDAR program from the International Space Station. We have ISAT, we have land cover, and then for buildings, we have lots of different things, from night lights to population data, built-up areas, settlement footprints. And then we've also included some image filtering. So some of these data sets are quite noisy. So we can denoise them and also create some edge filters just to sharpen up the data. So all in all, we have 15 different predictors for forests and 14 different ones for urban areas. Next slide, please. Next, we need to get some reference elevation data. So we take this from high quality LiDAR, and we've done this for 12 different countries. And why we chose so many countries was a simple reason that we need to capture as many urban landscapes and climatic zones as possible. So, for instance, if we just trained our model on LiDAR from Bristol, we might be very good at correcting for Victorian houses and your end of terrace or your terrace houses that you see from a typical British landscape. But that's not really going to hold it when you're trying to correct for skyscrapers in megacities or urban sprawl areas, say in developing cities. So what we need to try to do is get as broad range as possible. This is kind of a step from what previous studies have done, which typically just focused on one or two very local locations. This, of course, is a challenge because LiDAR is not available for a vast majority of places. So yeah, we've got a good range, and as soon as more LiDAR gets released, we'll kind of continually update this. Next slide, please. Step 2 is the actual correction. So we separated this into forest and building corrections. So you could probably just about see on these schematics is dotted lines, horizontal lines. So this is the elevation from the Copernicus DEM. So as you can see, it's typically on above buildings or kind of within trees. and from the random forest, we can kind of correct these for these two separate entities. Next slide, please. And then the first stage is post-processing. So we merge these two together, the forest and building, taking the minimum height, and then we apply several image filters. Why we do this is because sometimes the random random forest kind of overcorrects or maybe undercorrects something. So in this example on the right hand side here, you can see some trees in the middle, and these black solid lines are kind of below the ground surface, so creating pits. However, the pinky purple horizontal line is the correction from the merged post-processed. So yeah, and it was quite challenging doing this, because if you're a bit too aggressive with your filters, you kind of smooth out the DM and you kind of lose the benefits of having a 30-meter product. You might as well just be using merit or something similar, but you need to be aggressive enough that you manage to get out these artifacts which are undesirable. Next slide, please. So yeah, I'm going to finish up by asking what makes FabDEM different from other global DEMs. So quite simply, it's the first global DEM to remove both forest and building artifacts. It has complete global coverage, unlike some of the original SRTM products, for instance. It's the first terrain map at 30-meter resolution. So Merit was the first at 90-meter, and we are the first at 30-meter. I should say with the global coverage, we don't have Armenia and Azerbaijan, and that's because that's not included in the Copernicus DM. So yeah, they basically weren't allowed to publish that. But as soon as that does become available, that will be updated, of course. And lastly, we use a wide range of reference data from machine learning, and this is really kind of a nice feature of this study. Yeah, so now I'm going to pass you over to Peter Ewing, who's going to kind of visualize what these differences mean, essentially. Thank you.
Yeah, thanks, Laurence. So yeah, that was a good introduction to how we produce FabDEM, and yeah, I'm going to sort of continue that with showing how FabDEM looks, basically. But to introduce myself, I'm a senior developer at Fathom. My background is in climate change and flood modeling, but yeah, I've also been interested in other sort of big data projects, looking at satellite and trained data, which is sort of why I ended up doing this FabDEM project. And I previously also did my PhD at the University of Bristol. Cool. So let's move on. Next slide, please, Gavin. So I'll start with showing an example of the buildings removal. So this is just a section of the FabDEM looking at an area of Paris, actually. And the top plot is the original Copernicus digital surface model, which you can see is quite noisy, and a lot of that noise is coming from basically the heights of, or the differing heights of different buildings across the city. And in the bottom plot, FabDEM is a lot smoother, and the elevations have been reduced to where we're removing the building height elevations. I guess one thing to note is that you could say, in a sense, that the original Copernicus DEM does look like it's higher resolution, but actually that detail in it is, for many purposes and our particular purpose, is something that's quite undesirable. It's actually getting in the way of seeing the underlying terrain. So that's what we're doing with FabDEM. And to give you an idea of the error statistics, we computed some against some LiDAR data where, not for this particular spot, but over a wider range, and the median error from building heights in the LiDAR was 0.86 meters, which was reduced to only 8 centimeters in the FabDEM, and the mean absolute error was also reduced, as you can see. Next slide, please, Gavin. So similarly, I'm plotting an area here of some river channels, and one thing you notice along the river channel, which is this is showing the elevation. So the blue areas are the lower elevations, and the yellow areas are the higher elevations. And you can see along the blue river channel, you see bits of yellow in the Copernicus Dam, which is due to trees raising the elevation artificially in the Copernicus Dam. And as you can see in the bottom plot, with all of those yellow areas along the river are quite nicely removed in FabDEM, showing that our correction is doing what we want it to do. And again, looking at the statistics, you can see, from forest heights, the median error in those forested regions was around 3 meters from the original Copernicus DEM, and that's reduced right down in the FabDEM. And similarly, the mean absolute errors reduced. Next slide. So as Laurence was saying, I think we would consider previously merit DM to be the most suitable or the best option of global terrain data sets for our purposes. And so that's been the focus of our comparison. So here's a comparison around Rockhampton, Australia, comparing merit on the left, which you can see looks, you can see sort of grainy areas and a bit of noise and that sort of thing. And when you look in the middle, you see FabDEM shows much clearer parts of the floodplain, sort of flow paths where there's the sections of the different river channels flowing through. And on the right-hand side is LiDAR, high quality local LiDAR. And actually, you can sort of see the LiDAR is definitely crisper than FabDEM, but really there's not any substantial differences that you would sort of pick out and say FabDEM's missing in this example. So I think we're doing a pretty good job here. Next slide, please, Gavin. Just back one. And similarly, there's a similar example here, but in St. Louis in America. You can't really read the label, sorry, but the panels are the same. So merit's on the left, FabDEM's in the middle, and the LiDAR high quality terrain data is on the right. And again, there's quite a lot of sort of noise and sort of speckle that you see in the merit, which when you go to FabDEM, you can see the features and the contours of the terrain look cleaner and more realistic anyway. So in addition, I guess towards the bottom of the areas, sort of the center of St. Louis, and there's a few areas where the terrain, you can tell raised up areas from merit have been removed, which is a result of the cleaning up of the Copernicus Dam into FabDEM. Next slide. So to move away a little bit from just pure digital elevation comparisons. What we do at Fathom is flood modeling. So I guess something quite useful is to us to show you a flooding example. And this is looking at the area around Jakarta, which is a very flood-prone area. It's driven by huge amounts of monsoon rainfall. It's low-lying on the coast, and it's affected by severe issues with land subsidence. So yeah, this is going to only in the future cause greater issues with flood risk in Jakarta. So it's an important place to understand the flood risk. And I guess just to give a bit of context of the picture, I've plotted in colours of green to yellow to white the terrain. So the hills are the higher elevations at the bottom, and then going towards the top of the picture to the north is the lower terrain where the city is, and then the coastline is just to the north above the top of this image. And so the rivers are flowing from the bottom to the top. And yeah, so here, you in both cases you see the flooding from the rivers, but there's a lot finer detail in the connectivity of the floodplain. I think in the FabDEM flooding image, whereas in the FabDEM comparison from our older simulations, you can see sort of there's a bit of discontinuities where the bits of the floodplain aren't joined up as much. And in addition, I've highlighted on the right side here, there's a canal, which is a defensive flood defense canal, which basically it has been built in Jakarta to direct the water around the city, so the flood doesn't flow straight into the center of the city, but it sort of redirects some of the flow around the city. And there's a canal actually on the western side too, which has the same effect. And that's quite important because it's reducing the flood risk in the center. And you can see we have in the FabDEM sort of lower amounts of flooding at the top, which is the center of Jakarta, and instead have the flooding, being directed along the canal. So yeah, we're really happy with how these results are looking so far in FabDEM. And just going back a step, what I'm showing here is riverine flooding. And when we go to the next slide, then at Fathom we separately calculate riverine flowing, which was the previous slide, and then what we're showing here is flash flooding, which is from rainfall directly onto the terrain surface from very severe heavy rainfall events, and these are much more localized and much more widespread because you get heavy rainfall events everywhere, whereas they don't have to just be next to a river. And yeah, the FabDEM example shows, I guess because it's, we're picking up more detail, we're also seeing sort of smaller flow paths and more locations where we're getting this flash flooding sort of combining into floods. So that's an interesting result we're seeing here with the increased improvement with FabDEM. Next slide. And for completeness, I've just included a slide here showing the combined total flood from the river flooding and the flash flooding. Next slide. And yeah, so finally, one more example from Fathom, which is from an event response of Cyclone Batsirai, which happened in Madagascar in February this year. And we had a look at the basically the forecast of this cyclone and produced flood maps. This was led by James Savage at Fathom, and produced forecasts of what we thought the flood would look like for this event. And then afterwards, we've validated this flood event from satellite-based estimates of the flood. And you can see here, again, we've got much clearer correspondence with the FabDEM plot, which is on the right-hand side, where you've got the blue flooding areas matching up and covering the red observed flood extent, whereas in the merit based flood map on the left, where missing a lot of the flood, and it's not just not matching quite as nicely. So I think that's all from me. You can also read a bit more about the write-up of this event response, which is on our website. And I think with that, I'll pass back to Gavin.
Great, Pete. Thank you very much for that. And thank you, Laurence, for going through the development of FabDEM. And I'm sure there will be some questions. We've had a couple of questions come through on the chat. If you could put them into the Q&A panel, then I can collate the questions and we can go through them later on after my last couple of slides. So what I wanted to talk about, we've talked about science and the background and the development of the data set. Is really saying, okay, well, how do we apply the data set? It's that so what question for some of you out there on the engineering side, that this data may be useful and you wish to apply it. Well, that's engineering or, of course, academic research. So I think one of the key things is really looking at where the FabDEM sweet spot is. Pete has got some great examples there, comparing merit data, which is obviously derived from SRTM, and comparing that to LiDAR. So we really fit in the middle. We're not looking to compete with locally sourced LiDAR data or even boots on the ground site survey. That is really quite a different entity. But where we do have an impact is if you're doing a review of a project, or you're doing an early phase assessment of sites, or it could be master planning. You could have a 35,000 square kilometre zone in the middle of Saudi Arabia that potentially you can't get access to local terrain data. So with FabDEM, it's here, it's available now. It's actually, you could very quickly do your initial site assessment, and that will help you make much more informed decisions as to how you take the project forward in relation to the aspect linked to the terrain of the data. So it's very much in that localized view of data, but that is easily accessible at higher resolution, 30-meter resolution. And one of the other elements that I think one of the guys touched on earlier is that actually the FabDEM data is much more contemporary. SRTM is getting on for 22 years old. The FabDEM data is 5 years old. So obviously there's been a lot of change, particularly in developing countries, urbanization in that period. And so we're getting a much more contemporary perspective of the terrain. Okay, so let's just talk a little bit about some of the facts of FabDEM. Laurence mentioned that we actually have global coverage apart from Armenia and Azerbaijan. We provide the data in GeoTIFF file format, so rasters. Most of you deal with raster and GIS files, so it's very standard. We provide all our data out as GeoTIFFs. We've created it in 1 degree by 1 degree tiles globally. We actually package that up and zip that up to 10 degree by 10 degree tiles when we provide the data out to people. And that equates to about, for the 1 degree to 1 degree tiles, is 19,000 tiles. You can see the size of the data set there. And just picking up on some of the features or the metrics that Pete talked about earlier around mean absolute error, comparing FabDEM to Copernicus, and you can see there's a significant difference both when we're looking at the urban assessment and also a significant difference when we're looking at the forest side. So let's just turn now to typical applications for this type of terrain data set. As I mentioned earlier, and as Pete has alluded to, one of the key elements for any flood model is got to be the terrain data. So obvious application using this data on how you can apply this data to create flood models, local flood models or scheme models for cities or for territories. And then once you've created that model, it's using the flood models, ideally Fathom models, of course, in tandem with the terrain data to look at things like assessing single site analysis, or actually looking at a portfolio of assets. It could be in one country, it could be one region, it could be globally, to assess those assets in relation to flooding and terrain. It's also looking at spatial correlation. If you have a number of assets that are connected or fairly close together, they could be in the same river basin, they could be in the same river catchment. How are you establishing which assets are going to be less likely to flooding and or that are perhaps higher than the others? So it's looking at that spatial correlation to a particular flooding event and which assets could be impacted. One of the other areas we've had discussions with is around linear assets. That could be rail networks, road networks, but also pipelines and telecommunication networks, to understand the positioning of those and development of those networks in relation to flooding. And then also interconnected assets. It's all very well if you're looking at specific assets. So you could be utility, looking at a water treatment works or a valid pumping station that is in place to protect a city from flooding. But if the power supply gets knocked out because the substation half a kilometre down the road gets knocked out because it's more susceptible to flooding, then obviously you can put as much protection in, physical protection to protect from the flooding for that pumping station. But if the power gets knocked out, it's not gonna work. So looking at interconnected assets and using terrain and Fathom flood data is really important as well. And simple things like site access. Again, you might have very protected or a large site. That could be a manufacturing plant, it could be a warehouse, it could be a hospital or a campus for a university. So how do you get in and out of those sites? So that's related specifically to flooding, but of course it's much wider than that in the water arena. So looking at catchment management, how do you define and delineate catchments, potentially locating bodies of water, and also things like locating dams, looking at the height of dams, looking at the terrain around the dams and potentially the water level, and calculating volumes of water retained by dams. So that's one area that our data can be used in. So we've been focusing on water applications. Let's broaden that to a whole range of other applications that we've come across. I talked a little bit about master planning. That doesn't necessarily need to be related just to flooding. Of course, when you're looking at any master planning, you need to look at a whole range of particular issues, a lot of which are related to terrain. And so by having rapid access to detailed terrain data in regions that are probably data poor or data scarce, will help that decision-making process and speed that initial phase of the project up to help you understand where the issues lie within that particular site. The same with route planning or linear assets for new rail or road installations, or it could be pipelines for energy or in relation to communications and telecom networks. It's line of sight as well, which is very important. We've done some work with a number of organisations in the US around the siting of solar farms, and of course it's not just the access and the terrain for the particular site, but of course it's the orientation as well to ensure that that particular site provides the maximum exposure to the sun during the day and during the year, because obviously that's going to be pretty important if the solar farm is going to be effective. Another consideration that we've been engaged in is around landslide modelling, understanding the typical locations or areas that may be susceptible to landslide, and helping model that and determine which are the most susceptible locations. And then we start getting into things like agriculture and food production, again, where terrain and looking at height and the changing terrain over different areas, different fields, and particularly in relation to perhaps different crops and their suitability for different regions is important. And also this is going to play a key part as, of course, with climate change as well. As the climate changes, different crops will be more suited might be more suited to new areas, but also where existing areas might be impacted because there might be drought or they might be too high and not get enough sun or heat to help them grow. So beyond that, from agriculture, then obviously into forestry. Laurence talked a lot about forestry information and data, and there's a lot of information there that can be applied. We're talking about access, so the data can be accessed for research applications on the University of Bristol website at data.briz, and for non-research applications then please contact us at Fathom, and we can provide the data in either globally, regionally or country, and we have a variety of different pricing models around that. Okay, so you want to know more about the data, we have the research paper that we talked about. If you need to know more about the sample data, please contact us at FabDEM.global or any other inquiries related to that. This is the paper that we talked about, and we've got a variety of different other elements we can show you. I'm just conscious of the time, and we've got a few questions to go through. And so let me talk about couple of questions here. With ongoing urbanisation, what is the anticipated update frequency for FabDEM? I think you mentioned a little bit around this earlier, Laurence, didn't you?
Yeah, we haven't got a hard fast plan yet, but yeah, we do plan to update this as more predictive data comes in, gets updated, and we might new machine learning methods perhaps. Just kind of when we get around to it, really. But it is a plan.
Okay.
And can I jump in? I'll add to that one as well. Holly mentioned urbanization, and actually, I guess one of the key things with FabDEM is that we're trying to represent the ground level regardless of what the buildings are. So actually changes in urbanization shouldn't affect too much the actual terrain heights, because what the aim is for FabDEM is actually to show what the height is without the buildings. So for that sort of thing, the main benefits of updating is if we have new training data or new better predictors. So say if we have a better new data set that comes out which has amazing granular information about actually what the building heights are at every location of the world, or a better data set to describe how high the forests are in particular areas and that sort of thing. So that's what we would include, as well as improvements in their methodology in future updates. Pass back to you, Gavin. Thanks.
Thanks, Pete. Just conscious of the time. Well, we've got a few more questions that we'll try and answer, and if people are able to stay on, then that's great. One of the things that questions we've had is around getting access to the data, and do people have to have the global data set, or can we package it out? So the answer to that is no, you don't have to take the global data set. We can actually cut the data to your particular requirements, whether that's at a city level or a country level, or indeed for a specific site level. So we can provide that. Another question talking about, we showed a plot of flash flooding. Will flash flooding maps be available to download? So we at Fathom provide those maps for flash flooding. So if you are interested in obtaining maps to understand the impact of flash flooding, then please come to us directly on that. Let's see what other questions we have. Okay, we've got, do we have a comparison with DSM from JAXA, so a 30-meter resolution globally? I wonder, Laurence, if you could answer that one.
No, we didn't include that in this paper. So that is a DSM, remember, so this is the digital surface model, and we've created a digital terrain model. In other work I've been involved with we found it to be not that great, that JAXA product, in a few areas that we've been looking at. But that doesn't mean that for the particular area that you're looking at, that it might be suitable. So what I would recommend is to have a go at FabDEM, have a go at the JAXA products, and kind of see what's suitable for you.
Great. Okay. Well, as I said, just conscious of the time, we're overrunning. So I'd just like to wrap this up and thank you everyone for attending. We've covered a lot here. Just one element that I would like to share, that we do have this is a web viewer we have for FabDEM that goes through the comparisons between SRTM, Merit, and FabDEM for a number of different locations, and you can see a significant difference here. This is the Mekong Delta in Vietnam, and we have a number of other locations across the US as well. So if you would like access to this viewer and to share with your colleagues, to look at various examples of the data, then please contact us at that email address, and we can provide that information to you. We are, as I mentioned, we're launching our new Global 3 data later on this year. If you are interested in hearing more about that when we're able to release it, then please let us know.